So the theory, so for a matrix, if you have a positive definite matrix, it has an eigenvector decomposition. And it's true for infinite dimensional setting as well. This compactness is really important here. The fact that we're on a bounded interval, and this thing is a bounded function of t and s. I feel more comfortable saying continuous. That's really crucial. But then it's like a piece of cake. The proof is not that different than the finite dimensional case to prove this. So there are eigenfunctions. Which are orthonormal, okay? You know, so fi dot fj and their eigenvalues and this is what we're going to use to do this. So basically, then for x hat, you just go through and you write down this thing down. Well. There it is. Okay, so basically you have to construct these damned eigenfunctions, which you'll do approximately, and you usually do this empirically. You take data and you just look at eigenfunctions for the based on the data, and you're done with it. And this formula that I went through one direction is just how you define it, and you can check that all the statistics are satisfied. And what's more. Let's do it. So you can check that we already have done that. You can check that this is true. Hold on a second. Let's see what I want to say.
Is all this in what's called a reproducing kernel?
Nah. So the question was, does this have anything to do with reproducing kernel Hilbert spaces? And not at all. There's no overlap at all. That's another planet. Yeah.
Really?
Yeah. Absolutely. No. It's not. It's not. Yeah. Reproducing kernel Hilbert spaces are a beautiful subject, but those kernels have a very different, even stronger properties than this. Yeah. There's one more thing I wanted to say. So we said this, actually I forgot to say, it is interesting to look at the covariances as well. These are sometimes needed, and what are they? If you recall, it was equal to the dot product of what? It was the dot product of KFJ, if you look at your notes, and FI, which is strange, but things get reversed somehow. And KFJ is nothing but lambda JFJ. And then we have this orthogonality principle between these guys. And so that's why we get white noise. Okay? So the cross correlation is just the eigenvalue. And that's why these lambda i's are going to go to 0 fast. You know, they're going to just disappear. And so the cross correlation is going to disappear if you look at I and j far apart. You know, no, it's 0. Excuse me. I'm sorry, I got confused. No. The variance will go to 0. The variance will go to 0. Lambda is the variance. So because these are going to go to 0 quickly, and just like in Fourier series and all of that, under this continuity condition, they'll go to 0 quickly, and so you have that, and you can go through a little more work. You can see that I'm making some errors, so I'm not going to go and do it. But if you actually plug this in, you get another expression for this. If you go and you plug this formula back in, so I take the expectation of this by itself, because everything's white, when you take the expectation of the product, everything disappears except for the cross terms. So you just get I'll do it. Oh boy! So, if you actually do this, it looks like horrific, right? You know, but the F's are not random. It's only theCij's that are random. We have this beautiful formula for the cross correlation of these guys. It's white, so you just get lambdas. So you can stick to I equals j because all the cross terms are 0. And there's a star missing. I think somebody said that. So Ci dot Cj is what I just said is lambda phi equals j. And then I've got Fi of t. And then I've got Fi of s, because any cross terms disappear. But of course there's a star there. So the correlation function can be expanded in this way. It's outer products in a sense. Right. And this is known as Mercer's theorem. You'll hear that a lot. If you take a signal processing course, this will come up. Right. Yeah. So the only gap, is basically the existence of these guys. And again, that's just sort of. I can give you a reference if you're interested, but I don't think I should do it here. I did it. I mean, I loved it. We even did the infinite horizon case, where this was defined on minus infinity to infinity, and nothing was compact, and there wasn't there was a continuum of eigenfunctions. You can even do that if you had a very brave student population and a brave professor. I loved that lecture, but the professor was nuts. I mean, he was going so fast. He would go through the blackboards a race, and he did that for 2 hours. And I drank extra coffee and sat right where you are, But I'm not going to. That was another time and another audience. What else do I want to say? So, so why again? There's lots of reasons why we do this. Again, for model reduction, these guys decay quickly, so we do a finite sum. And again, you take data you get, and you look at empirical estimates of this guy here, and you do some model reduction. You've got a simple model, and that's it. That's the main reason. And it's used in hypothesis testing, detection problems, like signal decomposition problems, all sorts of things. So you can just find a whole course on applying this to problems in signal processing. So it's not my field of expertise, but it's very, very important to a lot of people. That's it. We did linear theory. Yeah, I don't think I want to say anything more. So I think we'll close just a few minutes early today. And there's so many questions in the office hours, it's good to leave extra time for that. And you all got the message that I extended it 24 hours. So I'm going to just hold office hours tomorrow afternoon, Thursday afternoon, and have the homework due on Friday afternoon. All right, signing out.